25. Symposium B1, Advanced Materials for Adsorption and Photo-Assisted Degradation of Pollutants in Water. Removal of arsenic in the aqueous phase using a hybrid system of zeolite and iron oxide nanoparticles. Present the word. Alejandra Moreno Barcenas, Alejandra Garcia and Gloria Lourdes Dimas Rivera, Centro de Investigación en Materiales Avanzados Monterrey, Mexico. The contamination of water sources for human consumption is a problem of great importance. It is known as one of the most toxic elements and is identified as carcinogenic to humans. The intake of this metalloid could cause gastrointestinal and cardiovascular disorders, nervous system damage, and death. In Bangladesh, millions of people are at risk of drinking water with arsenic contamination. On the other hand, some states in the north of Mexico also have this problem. Groundwater is the source of an estimated 39% of drinking water in Mexico. In this country's arid regions, groundwater is the main source of water for household use. It is estimated that at least 1.5 million people in Mexico consume water with arsenic above 25 micrograms per liter, and about 150,000 people are exposed to much higher concentrations still. About 900,000 of those mostly located in the states of San Luis Potosí, Durango, Zacatecas, Jalisco, Chihuahua, and Sonora are exposed to even higher levels, 4,500 to 29,600 micrograms per liter of arsenic. Methodology. To obtain the moringa extract, soxhlet extraction was used. The iron, 3, and iron, 2, were dissolved in distilled water. The zeolite was added and left to stand for 24 hours. The mixture was heated to 60 to 70 degrees Celsius, and 20 milliliters of moringa extract was added. The pH was adjusted to 13 with sodium hydroxide. The mixture reacted for 40 minutes. Finally, the material was washed 3 times with distilled water and dried. Methodology for adsorption. A batch sorption experiment was carried out. 1 solution sets containing 0.350 mg per liter of arsenic, 3, water with initial pH values of 5, 7, and 9 were prepared under open conditions. 25 ml of arsenic solution was mixed with 5 grams of zeolite iron oxide. The suspension was then stirred continuously at room temperature for 4 hours. For the kinetic study, 25 ml of arsenic solution were mixed with 5 grams of zeolite iron oxide. The suspension was continuously stirred at room temperature for 5 minutes, 10 minutes, 20 minutes, 40 minutes, 60 minutes, 2, 4, 6, and 24 hours. The liquid samples were subsequently filtered and analyzed by ICP. Characterization results. In Figure 3. Showed scanning electron microscopy, Section A and B, iron oxide nanoparticles, Section C and D, surface of the zeolite pristine. In Figure 4. Section A and B, surface appearance of the zeolite iron oxide, and Section C, energy dispersive X-ray spectroscopy, and Table 1. Chemical composition of the hybrid. Figure 5. Section A, X-ray diffraction patterns of zeolite, zeolite iron oxide, and iron oxide nanoparticles. Section B, the percentage of arsenic removal as a function of time showed a maximum of 93%. Symbols show experimental data and the pseudo-second-order kinetic model. Section C, linear correlation of the experimental data with the pseudo-second-order model. Section D, adsorption isotherm arsenic 3 at 3 different pH values of 5, 7, and 9. Langmuir and Freundlich adsorption models are included in each case. Conclusion. In this work, the removal of arsenic using a zeolite iron oxide hybrid was presented. The synthesis used was a green route, the nanometric material was supported on clean optolalite. The use of this synthesis technique reduces waste and achieves a nanometric particle size. The arsenic retention percentage observed 93%, with second-order kinetic behavior. The isotherms showed that adsorption is enhanced at basic pH, while at acidic pH, adsorption decreases. The adsorption process correlates with the Freundlich model, indicating that it is a nonlinear adsorption. Acknowledgement. The authors thank Dra. Nayeli Pineda Aguilar, Dra. Isabel Mendival, Dr. Alonso Concha, and Master Julio A. Rivera Haro at Centro de Investigación en Materiales Avanzados for infrastructure, technical support, and CICID by the support provided. Thank you.